Okay, it's 12:10 now, so we'll start the presentation. Hi everyone, welcome to the first seminar of the term. The presenter for today is Dr. Lama from Ryerson University, where she did her PhD research on investigating the impact of employing intelligent vehicles in distributed routing environment. And now she is a postdoc researcher there, focusing on developing predictive models for climatic variables to help structural engineers proactively design concrete structures while considering the impact of climate change. And the topic she will be presenting today is the prediction of greenhouse gas emission in downtown Toronto using deep sequence learning. Let's welcome Dr. Lama to present.
Thank you very much. Thank you everyone for inviting me. So as Nora said, the title for this webinar is the prediction of greenhouse gas emissions in downtown Toronto using deep sequence learning. So as you can see here, this is the paper that we worked on in collaboration with University of Toronto with Ran Tu. I think most of you know her, and Professor Marianne. So if you want to go back to the paper to get further details, you're more than welcome to check. For this presentation, I'll start with the overview and objective of this study, followed by a brief literature review, and then I'll share with you the specifications of the traffic and emission simulators that we adopted in this study. Then we'll start with the case study, methodology, data collection, results and discussion, conclusion, and future work. Let's start with the overview. So there are two facts that mainly. The first, transportation systems have been consistently ranked as the largest source of greenhouse gas emissions in the United States and in Canada. The second fact is that anticipatory routing has the potential to outperform myopic routing. When we say anticipatory routing, we mean that the cost on link for routing should be predicted of a future time step, while myopic or reactive routing requires that the cost at the current time step or a previous time step. So this triggered the need for predictive models to route vehicles proactively. In terms of the objectives of this study, we actually had 4 objectives. The first one was the development of a deep learning framework based on long short-term memory to predict greenhouse gas emissions in CO2 equivalents at link level at every minute in a highly congested urban network while utilizing microscopic data points. The second objective was systematic analysis of the importance of various predictors that were adopted in the developed models. The third objective was comparison of the results with 2 commonly used emission predictive models, autoregressive ARIMA and clustering, an illustration of the strengths and limitations associated with each model. The last objective was demonstration of the impact of the systematic tuning while applying LSTM. Moving to a brief literature. Generally, we found that greenhouse gas emissions were predicted at an aggregated level, spatially and temporally. In other words, this means that greenhouse gas emissions were predicted at national level annually. And this is something not suitable for dynamic applications such as routing vehicles. The second point that we found in the literature was that greenhouse gas emissions were mainly predicted based on fuel and economical factors. And this is due to the low level of spatial and temporal resolution. We also found that ARIMA and clustering were among the tools used for predicting greenhouse gas emissions. The last point, and which was the very important point that we found, is that neural networks outperformed other predictive models when used for predicting environmental pollutants. And this is our focus in this research work. Moving to the traffic and emission simulators that we adopted for this study, we chose to use microscopic level of resolution to capture every second, the details of every second. So in other words, we chose a microscopic agent-based traffic flow model that adopted the intelligent driver model to capture the second-by-second traffic characteristics of vehicles in the network. We also, to maintain the consistency actually in terms of the level of resolution, we adopted motor vehicle emission simulator moves to estimate the second-by-second greenhouse gas emissions in CO2 equivalents. This figure illustrates the interaction between the traffic simulator and emission simulator. So as you can see here that the main outcome of the traffic simulator was acceleration and speed, position, and so on of every second. Then in terms of the emission simulator, the first step was finding the vehicle power for every vehicle at every second. And this requires the outcome of the two outcomes actually of the traffic simulator, acceleration and speed, in addition to 4 parameters: rolling resistance factor, rotational resistance factor, aerodynamic drag factor, and the vehicle mass according to its type. Then we had to estimate the operating mode of every vehicle at every second. Finally, the outcome of the emission simulator was estimating emission rate, gram per second, of every vehicle at every second using the operating mode and using the vehicle type and vehicle year of make. Moving to the case study, unlike most of the studies that we found in the literature that adopt segments on highways, we chose downtown Toronto, which is an urban network and is associated with a high level of complexity. Our case study consists of 223 links and 76 nodes, which is downtown Toronto, the core actually of downtown Toronto. In terms of the demand, we chose the morning peak period between 7:45 and 8 a.m., which is a highly congested period of the day. Before I illustrate the steps that we followed for every model and in this study in general, I would like to clarify 2 important points. The first one is that most of you know that greenhouse gas emissions include carbon dioxide, methane, and nitrous oxide. Greenhouse gas emissions combined are more harmful to the environment than CO2 alone. And this makes us, actually made us predict greenhouse gas emissions instead of CO2 alone. The second point that I would like to clarify is that why we chose to predict the greenhouse gas emission rate gram per second. This is a very important point. It has been found that the marginal cost is the best form of cost at link level. The link greenhouse gas emission marginal cost is the produced greenhouse gas emission by one vehicle traversing a studied link. And this means that to estimate the marginal cost at a link, let's say, we need a greenhouse gas emission rate at that link at that time interval, multiplied by the predicted or estimated travel time at that link for that specific time interval. Moving to the general methodology of this study, the first thing we did is that we extracted data points at the second-by-second level from the microscopic traffic and emission simulators. Then we had to aggregate the second-by-second data points to be at link level at every minute. So at every minute, at every link, we I'll share with you later. So after we defined the link level at every minute, we conducted a correlation analysis between the traffic variables at the last 5 minutes and greenhouse gas emission rate at the 6th minute. This correlation analysis was our guide to define the optimal set of predictors and the best specifically LSTM. Here there was an iterative process where we had to choose different combinations of predictors and number of sequences to predict the greenhouse gas emission at the next time step, future time step, using the 3 models. And then we had a comparison, and then finally we chose the best model for prediction. So I'll give you an example to improve your understanding. So let's say we wanted to try a set of 2 predictors, speed and density, for the last 2 minutes, let's say 2 sequences. When I say sequences, I mean minutes, last 2 minutes. So this means that in order to predict, we had to have speed and density on that link for the last 2 minutes to predict the future value of greenhouse gas emission rates. Moving to the steps that we followed for every link, I'll start with ARIMA, which is a statistical approach with exogenous variables. So this methodology is applied for every link. You have to note that ARIMA lacks the spatial dimension. It means that it's not scalable. It means that we had to develop a model for every link. So all of the models, we divided the data into training to validation, 80 to 20% respectively. So here is what we did. For every link, we took the 80% data points. We had an iterative process to define the optimal combinations for autoregressive, integrated, and moving average. And then after we had the optimal set, we predicted using the 20% validation data set, and we combined the true and the predicted values of 4 lengths for a comparison with other models, and we plotted, predicted with the other models. Moving to the methodology we followed for clustering. Before I share this, I'd like to tell you that we had to define the number of clusters that we wanted to investigate, and this is something I'll illustrate later this presentation. So let's say we have k number of clusters. We divided the data again into 80 to 20% training to validation respectively. To overcome overfitting, or to take it into account, we adopted a cross-validation process where we had 100 iterations of cross-validation to make sure that we chose the optimal emission rate for every cluster. So what we did is that we divided the data 80% to 70 and 10%. We defined the optimal emission rate of the 70% data points based on the factor, which is the least true minus estimated. After we defined the optimal emission rate, we used it to predict using the training, or to make sure that it is the best emission rate. And we did the same, we applied the same factor, which is the least true minus estimated emission rate. After 100 iterations, we chose the emission rate, the optimal one for every cluster. We used it to predict using the validation, 20%. We compared then with the other models. Moving to LSTM, which was our main concentration in this presentation. For LSTM, we had two stages. The first one was the manual tuning, and the second stage was the systematic tuning. So for the manual tuning, what we did is that we had different combinations of predictors, number of sequences, and set of parameters. So we put them in the network, we trained the network, we used the testing set to predict, we checked the results, and we kept on trying different combinations of these inputs till we got kind of satisfying results or good results. And then we had to stop at a point where we didn't get better results. So you will ask me now, what is the relationship between systematic tuning and manual tuning between these two stages? So basically what we did is that after we did the manual tuning, we took the optimal values of the hyperparameters and we set our ranges for search for the systematic tuning for Bayesian optimization. So for the systematic tuning, we used a Bayesian optimization. We had to define the ranges, and this was defined based on the manual tuning outcome. And we had to define the time for optimization. In our case, I remember the longest period was 4 days to systematically tune the hyperparameters. And then after we trained the network, we tuned the hyperparameters, we predicted, and we compared with the other models. Moving to the data collection, here you can see that we used the end-to-end connected and automated vehicle E2E CAV, which is a distributed routing framework. We used it to collect the microscopic data points. The E2E CAV adopts two types of communication, vehicle to infrastructure and infrastructure to infrastructure. In terms of the demand level, it was provided by Transportation Tomorrow survey. And there is something very important to share with you here. So in order to have good results and to train the network, LSTM network or the other models, well, we had to generate different conditions in the network. And this was happening, actually, this was assured by generating different demand levels. So based on the demand of 2014, we chose 70%, 10%, 130, 150, and 200% of that demand. And you can see here is the corresponding number of vehicles. And we use different departure time distributions. To ensure that we had different traffic conditions in the network, congested, uncongested, to have wide range of values for every predictor or every indicator that was used for the models. To be more specific, for ARIMA, the training to validation data sets consist of 66 and 17 data points, respectively. For clustering and LSTM, the training to validation data sets were of around 49,000 and 12,000 data points, respectively. In this slide, I would like to share with you the statistical analysis of the predictors, the most important predictors, top 3 predictors. This is for speed. As you can see in downtown Toronto, the speed ranges from 0 to 80 km per hour. You can see that the frequency is really high for values, let's say between 40 and 60, and it is really low for speed between 0 to 20, 60 to 80. For flow as well, vehicle per hour, you can see that the frequency ranges from, or the values ranges from 0 to 0.7 times 10 to the power of 4. Density per lane, the value ranges from 0 to around 150. Frequency is really low, starting, let's say, from 75 and till the end of the range. Here, this is very important to note for greenhouse gas emission rates in CO2 equivalent. The range is from 1 to around 5, or the actual true values were till 6. However, the frequency is really very low, starting from 4 to the end of the range. And this has an impact, actually it had an impact on the results, and this is something I'll share with you in the results section. As you can see here, moving now to the results and discussion, I'll start with the correlation analysis, which was a very important step in our research, where we conducted a comprehensive correlation analysis for indicators not only on studied links, but also on end links, because in the network, links are connected. So what happens on end links at time, let's say, t-1 indicates or implies what the conditions would be on the studied link at time t. So we chose 5 minutes, minute 1, 2, 3, 4, 5, and we investigated the correlation of these indicators with the greenhouse gas emission rate at the 6th minute. So we found, and as you can see here, that the correlation coefficient, there is an increase, the absolute value increases from minute 1 to minute 5 of all the indicators except for delay. And in terms of the outcome, the top highly correlated variables or indicators are speed, in order: speed, greenhouse gas emission rate, density, and in-link speed. These are the top four correlated variables with greenhouse gas emissions at the 6th minute. Moving to the results of the first predictive model, which was ARIMA, it is a statistical approach. It is important to note that we used for this model speed, the top highly correlated variables that are the top 3: speed, density, and greenhouse gas emission rate. Number of sequences was 3. As you can see in the results here, this figure, so this is the results and discussion for the first model. As you can see here, that we chose for this model the top 3 highly correlated predictors: speed, density, greenhouse gas emissions, for 3 sequences. This figure illustrates the performance of prediction for 4 links. So as you can see, on the x-axis we have the true value, on the y-axis we have the predicted value of a greenhouse gas emission rate. We chose 4 performance indicators: correlation coefficient, fit to the linear curve, R-square, and root mean square error. As you can see, and it's very important to note that ARIMA lacks the spatial dimension. In other words, it means that it's not suitable for large case study, it's not scalable. We had to develop a model for every link, and this is a major limitation. Moving to the second model, which is clustering. For clustering, what we did, the first thing is that to define the optimal number of clusters. According to this figure, which is the elbow method, we sum of squared error value. We investigated till 15 clusters. According to this figure, 5 clusters is supposed to be the optimal. However, we chose to investigate the impact of employing 10 and 15 clusters to improve actually the prediction performance. Moving to the results, we use the same predictors: speed, density, and greenhouse gas emission. Here you can see that there is 5 clusters, 10 clusters, and 15 clusters. We use the same performance indicators. On the x-axis, again, we have the true value. On the y-axis, we have the predicted values of greenhouse gas emission rate. The instant thing to note here is that greenhouse gas emission rate was considered as a discrete variable. So as you can see, values between 2.5 and 4 in this figure estimated to be 2.5 or 4, or overestimated to be 4. This is a major limitation, and this means that although clustering considers the spatial dimension and it is scalable, however, it didn't consider the dynamic nature and temporal dimension properly compared to ARIMA, let's say. So looking at the results, employing 10 clusters and 15 clusters contributed to reductions in the root mean square error of around 3.1 and 3.5% respectively, compared to the case of 5 clusters. Moving and discussion related to LSTM, we chose two solvers, the stochastic gradient descent with momentum and adaptive moment estimation ADAM. In terms of the hyperparameters, we considered initial learning rate, momentum, max epochs, learning rate drop factor, learning rate drop period, number of hidden units of the first LSTM layer, and number of hidden units for the second LSTM layer when used. Moving now to the major part of this presentation, which is related to the results of LSTM. So what I did here is that this LSTM was used for comparison between LSTM and the ARIMA and clustering. We used the same predictors, speed, density, and greenhouse gas emission rate for the last three sequences, or minutes in other words, while using one hidden layer. So we used the same performance indicators. X-axis is for true value, Y-axis is for predicted value. The interesting thing to note here is that LSTM has overcome actually the limitations of both ARIMA and clustering. LSTM considered greenhouse gas emission rate as a continuous variable, unlike clustering, and is scalable, unlike ARIMA. We need to do a comparison between systematically tuning the hyperparameters and manually tuning the hyperparameters. You can see that there is a clear improvement in terms of the whole performance indicators compared to the manually tuning. Specifically, root mean squared error has been reduced by around 17% compared to the case of manually tuning the hyperparameters. So in terms of the performance, if we want to compare LSTM to ARIMA and clustering, root mean squared error has been reduced by around 37% and 3% compared to ARIMA and the best clustering model. Moving to the second LSTM model, we use here a speed, density, and a greenhouse gas emission rate, in addition to the highly correlated in-link variable, which is in-link speed, for three sequences and for one hidden layer. There is an improvement here if you want to compare this network that is systematically tuned to LSTM1 that was systematically tuned. There is a slight enhancement in terms of the whole performance indicators, and we can see the same trend when we compare systematically tuning to manually tuning the LSTM network. There is a reduction of around 16% in terms of the root mean squared error when systematically tuning the hyperparameters compared to manually tuning the hyperparameters of the network. So in terms of root mean squared error compared to LSTM1, the improvement is negligible. However, we wanted to consider the spatial dimension and to consider that links are linked together. So what happens on in-links at time t-1 indicates what the conditions would be at the studied link at time t. Moving to the next last LSTM network, we use the same performance indicators. True value is on x-axis and predicted value on the y-axis. The main difference between LSTM2 and LSTM1 is that we increase the number of hidden layers to improve the prediction performance. And here you can see that when we compare systematically tuning with manually tuning the hyperparameters, we can see significant improvements in terms of the whole performance indicators. As you can see, that root mean squared error has improved by around 26% compared to the case of manually tuning the hyperparameters. And this is one of the objectives of this study, to show the importance of systematically tuning. This network is the best, and this network can be used for prediction let's say for routing applications. There is one very important point to share with you. As you can see here, that in all of the figures, the greenhouse predicted, and there is, and this is what I would like to illustrate in the next slide. Looking here at the statistical analysis, briefly, you can see that the frequency of greenhouse gas emission rates that are greater than 4 is really very low. And this contributed to the poor prediction performance for values greater than 4, as I illustrated in the previous figure and the ones even before. High greenhouse gas emission rates are associated with either low speed or high speed, and this is also illustrated in the frequency figure of speed in the network. Comparing the results quickly, ARIMA was the worst, then comes clustering. With increasing the number of clusters, the performance has improved. Then LSTM, it outperformed both ARIMA and the best case of clustering. When we incorporated the in-link characteristic, which is speed, there was a slight improvement, increasing the depth of an LSTM also was associated with a slight enhancement. In conclusion, LSTM has outperformed both ARIMA and clustering. More specifically, the root mean squared error of the LSTM that was used for a comparison has been improved by 37%, 3% compared to ARIMA, and the best case of clustering. While LSTM can scale up to a network level and considered greenhouse gas emission as a continuous variable, ARIMA required a model for every link, and clustering considered greenhouse gas emission rate as a discrete variable. ARIMA major drawback is related to scaling and nonlinearity consideration between variables. Clustering's main limitation is that predicted greenhouse gas emissions was considered as a discrete variable that contributed to over or underestimation of the predicted values. For future work, proactive single and multi-objective eco routing should replace reactive routing for less greenhouse gas emissions in future. This is a study that we conducted. If you would like to check it, you are more than welcome to do so. We compared between proactive single and multi-objective routing, reactive single and multi-objective routing, and we really got very good results. We used our sophisticated predictive models for this study, and we got very promising results for using predicted values while routing vehicles. For future, generating more data points that reflect on the less captured conditions would contribute positively to the current outcome. Dedicating more time for the Bayesian optimization process to tune the hyperparameters may contribute to higher level of accuracy of prediction. Developing predictive models for highways and expanding the case studies would be an added value. Finally, applying the developed predictive models while using real data is of high importance to validate the developed framework. Thank you for listening.
Thank you, Dr. Lama, for the presentation. We'll open the floor to anyone if anyone have any questions. If you have a question, you can raise your hand using the raise hand button, and I'll promote you to a presenter to ask your question. Does anyone have any questions? Anyone? We still have 10 minutes. We can ask, if you have questions, we can ask now.
Yeah, for sure. Anything.
Yes, Emily, I'll promote you to a presenter so that you can turn on your mic. Okay, Emily, can you try to turn on your mic now?
Hello. Thank you for the presentation. I was curious if you ever use like longer time spans for prediction, like further into the past, and also is the main practical application of the models to be used for eco routing? Like, does it have any other practical applications?
So thank you for your questions. So the first thing is that according to the length of the links in the network, so the maximum length of a link in our network was around 450 meters. And according to the free flow speed, so the maximum or the minimum time to traverse a link was 0.8 minutes. So we chose 5 minutes, and we trust that it was more than enough to be captured, because more than 5 minutes, I don't think there is an impact of, let's say, the temperature dimension on the greenhouse gas emission at, let's say, the next time step. So this was by investigating different options, and we chose to take into account 5 minutes because we thought it is enough based on the given inputs of the link length and for the free flow speed. In terms of your question related to the application, so basically, I believe that at this stage, I'm not sure if there should be other applications that would benefit from these sophisticated predictive models. But what came to my mind, because we already had a paper related to single and multi-objective eco routing. So we at this stage, I believe like eco routing, proactive eco routing is the direct application that can benefit from these sophisticated predictive models.
Great, thank you.
No, more than welcome. Thank you for asking.
Yeah, thank you, Emily, for your question, and thank you, Dr. Lama, for the answer. Anyone else has any questions? Anyone? Okay, if sorry, if no one else has any question, this will be the end of the seminar today. Sorry. Thank you so much, Dr. Lama.
Allow me,
yeah.
I just have a message for the graduate students attending with us. We are going through unprecedented time, and I really want you to look at the positive. I have been through your experience because I graduated in August 2020 last year. So I've been through what you are going through now. I wish you all the best. Just take a look in the future and see yourself holding your degree. Be positive. Try to go and exercise. And my advice to you is to surround yourself with positive people to get positive energy. And I trust that you will all make it at the end, and you will be whole. Just a matter of time. Be resilient and consistency. Yeah, you'll do it.
Yeah, thank you so much, Dr. Lama, for the advice. Yeah, it is an unfortunate time, and it's also unfortunate that we can only host these seminars online. But hopefully we can get through this, and we'll be able to see each other very soon. So if no one else has any,
I hope so.
Yeah. If no one else has any more questions, this will be the end of the seminar today. Thank you everyone for joining us, and we'll see you next week. And thank you, Dr. Lama, for the presentation. And sorry for
more than welcome
for the situation happened with the disconnection of the internet.
Yeah, it's fine. It happens. Yeah.
Yeah. Thank you all.